Uh, Hello, dear students. Now, since we have completed our discussions on the first chapter of my portions, that is solutions, we are now going to take up the second chapter, the next chapter, that is phase rule. In fact, uh, phase rule is a topic which comes under the broader area of thermodynamics. And as soon as we hear, most of us, including me, the word thermodynamics, it's like it's like something terrible is going to happen to us, is it not? So this cartoon depicts that. Why I'm showing this cartoon is uh, finding difficulty with thermodynamics is not very personal. It's a uh, mindset universal mindset. Most of us find difficulty with thermodynamics. However, phase rule is one topic in thermodynamics which can be much more easily understood than actual hardcore thermodynamics chapters like your laws of thermodynamics or statistical thermodynamics, such things. So, all that we need to know to understand phase rule is a clear cut understanding of three important terms which is used in phase rule. So, now let us see what phase rule is first of all. Okay, we'll take an example. This picture shows water in three phases: the gaseous phase, we also call vapor, water vapor, the liquid water, and the ice. So now, uh, is there any other phase in which water can exist? No. These are the three phases in which water can exist. And when I tell phases, it is to be understood more as states, state of matter, solid, liquid, gas. However, uh, there is a minor difference between phase and state of matter, which we are going to discuss later. But as of now, let us consider the water is now existing in three phases. uh, you can see that the phases exist in equilibrium with each other. So let us consider water, which is contained in a bottle and stoppered. Don't you have vapor above the surface of water? Of course, yes. In fact, our whole previous chapter discussion was on vapor pressure, where a liquid gives out vapors on its surface and that vapor exerts pressure. But what we did not look into that aspect in the previous chapter is the equilibrium between those phases. We were just interested in vapors and the composition of vapors, those things there. But here we are looking into the equilibrium between these two phases. So even if you have water in a bottle and there is vapor above the surface of water, there is a dynamic equilibrium. What do you mean by this dynamic equilibrium? Dynamic equilibrium means an equilibrium which is okay. First of all, what is an equilibrium? Equilibrium is a state in which there is no change in the if it what is the chemical equilibrium? Chemical equilibrium means it's a phase of a reaction in which, or it's a time in which there is no net change in the concentration of reactant or the concentration of the product. The concentration of both of them appear to be constant. But is it constant because the reaction has stopped? No, the reaction is still going on. Then why is it constant? Because the rate at which reactants are formed is equal to rate at which reactants are, the rate at which products are formed is equal to rate at which products go back to reactants. So this is called dynamic equilibrium. Reaction is going on, still a state of equilibrium is apparent. We observe it as an equilibrium. So similarly, the gas and the liquid, the vapor and the liquid, they are in dynamic equilibrium. We say. What do you mean by this dynamic equilibrium? The gas, how is the gas formed? Because of the vaporization of the liquid. So this is the evaporation direction, vaporization direction. How is the liquid formed? Condensation of the gas. So in that setup where a water is enclosed in a bottle, water will be continuously evaporating into gas, vapor, and the vapor will be continuously condensing into liquid. water. But since the rates of condensation and vaporization are equal, we find the amount of liquid and vapors are constant. So there is an equilibrium. Gaseous molecules are condensing, liquid molecules are evaporating, there is an equilibrium. Similarly, an equilibrium can be reached between solid ice and water. For example, at 0 degrees Celsius, what can happen? Water will be freezing into ice. Ice will be melting into water. This is also a dynamic equilibrium. Either directions, the processes are going on. But why there is no net change in the amounts? Because the rates are equal. Now, it is easy to visualize two-phase equilibrium, where one is liquid, one is water, and an equilibrium is reached between them. But, or similarly, like solid and liquid, an equilibrium is reached between them. But now we have to just uh, think beyond this imagination and then venture into one more addition of one more phase to this equilibrium. In the sense, think now of an equilibrium which is set up amongst three phases. If it's two, it's easy. Solid, liquid, liquid. Now, amongst three phases. Example, this diagram, the water. There is gas, there is liquid, there is solid. That means there is ice, there is water vapor. And an equilibrium is present amongst all the phases. That means what? Gas is depositing into solid, gas is condensing into liquid. Look at the picture. You can see two equilibrium involving any one phase. You take liquid, there is gas on one side and there is solid on the other side. You take solid. What is the process of solid converting to gas directly called? Sublimation. Yeah. What is the usual route? The solid becomes liquid, liquid becomes gas. But the solids can also directly go into gas. Okay. So at least have you observed when we are fond of ice, I know ice creams. When you open the freezer box, you get that white fumes type. Is it not white smoke type? What is that basically? That is nothing but water vapor, dense water vapor. What is the source of the dense water vapor? Is the ice crystals which are deposited on the freezer box, or ice crystals which are deposited on your ice cream bowls. This is the source of that. That means what's happening there? There is no liquid. Ice is directly subliming into water vapor. So those things can happen. Therefore, now we are looking into equilibrium amongst more than two phases, three phases, in sometimes four phases, sometimes five phases. Of course, 4 and 5 phases are not possible with water, but with some other materials, it is possible. Some other compounds, it is possible. Anyway, now, what is the point here? That an equilibrium is existing amongst all phases. Okay, but we will see later that having all three phases at equilibrium at the same time is a very sensitive issue. That means the conditions have to be specified, very specified too much. Only then this equilibrium can exist. Otherwise, one of the phases will disappear. Anyway, we'll look at that later. Okay, so we understood this. Now I'll ask you a question. Is it a homogeneous equilibrium or heterogeneous equilibrium? Okay. First of all, let me tell you what is an homogeneous equilibrium. Equilibrium set up within a single phase is a homogeneous equilibrium. For example, the equilibrium of chemical reactions, which we do usually in a solvent, is a homogeneous equilibrium. Nitrogen plus hydrogen giving rise to ammonia. This is an equilibrium reaction, right? Haber's process. Think of Haber's process. Ammonia can decompose back into nitrogen plus hydrogen. But is it an homogeneous equilibrium or heterogeneous equilibrium? Homogeneous. Why? All the reactants and products are in gaseous phase, single phase. So within that single gaseous phase, molecules are dynamically converting into one another. That is homogeneous equilibrium. What is an heterogeneous equilibrium? Heterogeneous equilibrium is an equilibrium which involves different phases. Okay. So using this idea, if we can answer this question, the picture I have shown about the equilibrium of different states of water, is it homogeneous equilibrium or heterogeneous equilibrium? Obviously, The answer is it is an heterogeneous equilibrium. Why it is an heterogeneous equilibrium? Because it involves three different states, three different phases: gas, liquid, solid. So gas is converting to solid, solid is converting to gas, solid is converting to liquid. All possibilities are there. So it's a heterogeneous equilibrium. So why this heterogeneous equilibrium concept is important? Because the whole Gibbs rule, or the uh, Gibbs phase rule, not Gibbs rule, Gibbs phase rule, or phase diagrams, or are meant, the objective of this Gibbs phase rule, phase diagrams, is to make us better understand heterogeneous equilibria. Okay, that's a very important point. Phase rule enables us to understand heterogeneous equilibria. Okay, fine. So now let us uh, uh, understand the definitions of phase rule. Okay, so what are the characteristics of phase rules? It's an important tool, like as I told, quantitatively understand equilibria, particularly heterogeneous equilibria. Okay, and it enables us to predict the conditions we must to specify for a system to exhibit in equilibrium. This point we will discuss in depth later in our next discussions. Two or more different phases are present in equilibrium to form heterogeneous system. Such systems are studied by phase rule. This is the point we discussed in our previous slide. Heterogeneous equilibria are best studied, best understood by applying the principles of phase rule. Who formulated this? It was Willard Gibbs who formulated this phase rule in way back in 1876 on the basis of thermodynamics principle. In fact, like rules come with exceptions, is it not? There is a rule that all rules have exceptions, but this Gibbs phase rule is one unique rule which doesn't have any exception, provided we are not bringing the system under the influence of electrical field, magnetic field, or gravitational force. Otherwise, if we don't allow the influence of these fields on the system, this rule is universally applicable. This has no exceptions, in fact. A very unique rule, right? But Gibbs derived this in 1876, and later it has been used almost in the same version which the phase gave. The same version, the phase rule, has been used even till now. So it's been more than 150 years. Still, it's being used in the same version, phase rule. So these are the uniqueness of this phase rule. No exceptions. Okay, now let us go into the definition of phase rule. In a heterogeneous system in equilibrium, which is not affected by gravity, electrical, and magnetic fields, the number of degrees of freedom of a system is related to the number of the components of the system and the number of the phases in the system existing at equilibria by the formula. F is equal to C minus P plus 2. Okay, formula is very simple. It just involves three terms, F, C, and P. What is the relationship? F is equal to C minus P plus 2. What is F? Number of degrees of freedom. Components. Number of components is C. P is number of phases. And two additional variables of temperature and pressure. It's okay. Now, to understand this phase rule, first we must understand in a clear way, as I mentioned, what are the meanings of phases, freedoms, components. Okay, so let us first know what a phase is. Phase is defined as physically distinct, homogeneous, and mechanically separable part of a system. It should be physically distinct, means there should be a boundary between two phases. You should see a boundary between two phases. There can be any number of compounds in a phase, no problem, but they have to be homogeneous, then they all come under one phase. Even between two compounds or two phases of compounds, like water and ice, it's a single compound, water and ice, there is a distinct boundary, right? You can separate ice from water, you can separate water vapor from water. Therefore, They are all mechanically separable phases. Okay. Now, understand this through examples. Air. How many compounds are there in air? A lot of compounds, right? Nitrogen, hydrogen, sorry, not hydrogen, nitrogen, oxygen, water vapor, carbon dioxide, sulfur dioxide, nitrous oxides, helium to some extent. So these are all present in air. But how air constitute how many phases? Single phase. Why air is single phase? Because it is homogeneous. You cannot see a boundary between different gases, right? So air is an example of a single phase system, though it has too many compounds in it. Okay. Now, if you have homogeneous solutions of anything, gaseous mixtures are always homogeneous. So they all form single phase. Now you take a solution of two liquids. Air is an example of solutions of gases. I should not say solution of gases. It should be mixture of gases, but let us keep it like that. It's a solution of gases. Single phase, homogeneous, only one phase. What about two or more liquids which are miscible with one another? Like example, lot of examples we studied in our previous chapter, is it not? Water plus ethyl alcohol, chloroform plus benzene, benzene plus toluene, ether plus benzene. All these fully soluble liquids with each other, how many phases they give? Single phase. Because a solution is homogeneous. You cannot see boundaries within a solution, right? Okay. The same thing, if you take the example I have written here, water in liquid phase, liquid state, and water in water vapor state. How many phases? Two phases. Because water and gas, you can demarcate. You can see boundaries clearly, water and gas. So two phases. Okay. So this is how we have to identify the number of phases in the given system. In the given system, this is very important. You are not going to identify phases in whole universe. In the given system, see, thermodynamics is a chapter in which it is so system centric. You have to first define your system, identify your system, and then apply all your rules of thermodynamics on that system. Is it not? Therefore, system plus surrounding, all those things come up. Even in a phase, it's in the given system, how many phases are there? First job is to identify the number of phases. In fact, identifying number of phases is easier, much easier than identifying number of components and number of degrees of freedom. So first, let us do the easier thing first. So identify the number of phases in a given system always. Okay. Now, what do we mean by component? Component is not equal to compounds. Okay, component is not equal to compounds. Please remember this. Component is defined like this: minimum number of independent variable constituents which are required to express the composition of each phase in a system. Definition is very technical. No problem. We will let us understand number of components through examples and then come back to this definition. You will understand it better. So basically, there is a small guide to identify the number of components. That is, C is equal to N minus E, where C is the number of components, N is number of chemical species. This you can understand. Number of chemical species, you just identify how many different types of chemical compounds are there in the system. Total, in whichever phase, how many different type of chemical compounds are there in the system. That is N. And E is number of independent equations relating to the concentrations of the species. This I will explain it in the next slide. So, okay. So now let us consider this example. Water. I mean, water is a starting point, water system, to understand phase diagram. Okay. So repeatedly, I'll go back to the example of water in my slides. No problem. In water, first of all, how many phases? If the water is in equilibrium with ice, water, and water vapor, how many phases? Three phases. Is it not? Okay. How many components? How many components? In all three phases, it is the same chemical substance, water, H2O. You just look into the formula of the compounds, H2O. So it is a one component system. one component, and how many phases? Three phases. Okay, fine. So look at this. It is one component and three phases. Component water, water, water. So single component. Now, easier, right? Now I will take one more example of sulfur system. Okay, this sulfur can exist in four phases. Okay, please look at the difference here. In the water system, the phases meant three states of matter: liquid, solid, and gas. In sulfur, we call four phases. But what is the state of matters of the sulfur here? Solid, liquid sulfur, vapor sulfur. So it should be three phases, right? Similar to water. Why is an additional four phase we are talking of? Because in the solid phase there are two crystal structures. One is rhombic sulfur, the other is monoclinic sulfur, monocline sulfur, or monoclinic sulfur. These are the two phases in the solid phase. So how many phases in total? Four phases. Inside solid, there are two crystal structures. One is rhombic sulfur, the other is monoclinic sulfur. What about liquid? It is single liquid sulfur. What about vapor? Sulfur vapor. But how many components? Again, one component. Why? In all these four phases, it is the same sulfur atoms. So one component, four phase system. Therefore, in any given system, if you are able to identify the number of phases and the number of components, number of freedoms, degrees of freedom can be known by using phase rule. F is equal to C minus P plus 2. Okay, that is in fact the importance of phase rule, which we will talk about later. Okay, fine. We'll take a bit complicated example. The equilibrium between this is a chemical equilibrium, decomposition of calcium carbonate, chemical equilibrium. So at equilibrium, what are the three different compounds present? I'm not talking about components, compounds. Chemical equilibrium I'm talking of. What are the three different compounds present? Calcium carbonate, which has decomposed into calcium oxide and carbon dioxide. So this is a thermal decomposition. You can heat it and the products are formed, calcium oxide plus carbon dioxide. In metallurgy, this is also called calcination. You are going to heat a compound in absence of air. That is calcination. So if you can do the calcination of calcium carbonate, an equilibrium is set up at a particular temperature. So equilibrium is also temperature dependent. So at a particular temperature, the equilibrium is set up. Now, how many phases in this equilibrium? You tell me how many phases in this equilibrium. Okay. You have calcium carbonate, which is solid, and then you have calcium oxide, which is solid, and then you have carbon dioxide, which is gas. Don't mix calcium carbonate and calcium oxide into a single phase of solid. Not because calcium carbonate structure is different. Calcium oxide structure is different, although they are of solid. Therefore, calcium carbonate solid one phase, calcium oxide solid another phase, carbon dioxide gas another phase. So three phases are there in this system. How many compounds are there? Three compounds: calcium carbonate, calcium oxide, carbon dioxide. But how many components? In the phase rule, F is equal to C minus P plus 2. C stands for not number of compounds. Please understand. It stands for number of components. Now we are clarifying what this number of components is by this example. It appears there are three compounds, but the components is only two. How we arrived at this two number? Look at this slide. In the phase 1, which is the calcium carbonate phase, this is how number of components is decided. Okay, we have to write equations for each phase considering the compounds in all the phases. Is it possible to express the compound in each phase as combinations, additions or subtractions of the compounds in other phases, or total compounds present in the equilibrium? This is the point. Now let us take the phase calcium carbonate. That's solid phase, right? One phase. How to write calcium carbonate? You can write calcium carbonate is pure phase, that is calcium carbonate plus 0 calcium oxide. What is calcium oxide? 0 calcium carbonate plus calcium oxide. Fine, no problem. How to express the components of carbon dioxide phase, gaseous phase? You can simply write carbon dioxide as calcium carbonate minus calcium oxide. Okay. For calcium carbonate solid phase, was it possible to express calcium carbonate as combinations of other compounds? Not possible. Calcium oxide? Not possible. Is it possible to express carbon dioxide as combinations of other compounds? Yes. It is simply calcium carbonate minus calcium oxide. Okay. So, how many components now? 2 components. Why? Simply, this is where you have to identify, this is the important step point to understand identifying number of components. So what do you mean by components? Simply put, components are the number of chemical species you require, minimum number of chemical species you require to express the constituents of all phases. Okay, so how many number of chemical species you require to express the constituents of all phases? Only 2. Which are those? Calcium carbonate and calcium oxide. Using these 2, you can express the constituent of all phases. Like I have written the equations. Therefore, this equilibrium contains 2 components. Thermal decomposition of calcium carbonate contains 2 components. Now the number of degrees of freedom. Basically, the number of degrees of freedom means how many thermodynamic parameters do you require to define the equilibrium. Okay, minimum number of independent variables. These independent variables are basically the thermodynamic variables. See, which are the 3 basic thermodynamic variables? PVT, pressure, volume, temperature. All our thermodynamics laws are basically deduced from our understanding of gas laws. PV is equal to RT. So these are the 3 variables. Of course, there is one more variable, that is the amount or the concentration. These are the 4 variables. Pressure, temperature, volume, and the amount. These are the 4 variables. Now, I am going to write a system in equilibrium. I can add any number of phases I want in that equilibrium. But at the given temperature and pressure, can that equilibrium exist? This is the question. Can that equilibrium exist? This is the question. Now, the other way of looking at this is, okay, let us look in a positive side. In a positive version of this. I can write an equilibrium using any number of phases I want. I can write an equilibrium. Now, how many thermodynamic variables like temperature and pressure, or simply temperature and pressure, how many variables do you require to specify the value of temperature and the value of pressure? How many variables? Is it enough that you can define the system by fixing the temperature? Is it enough that I can define the system by fixing the pressure? Or is it that I have to fix both temperature and value and pressure value to define the system? This is the question. Okay, if I can fix only the temperature value to completely define the system, the system will exist at the temperature, whatever pressure. Okay, then it becomes single variable. Let us consider this as with an example. Now, water vapor, gas. There is no equilibrium. I have not considered any equilibrium. Pure gas I have taken. How many variables you require to define? If I tell I am having a container of gas in my hand, somebody can ask, what is the temperature at which you are having that gas? Is it not? Why? Because if you decrease the temperature, what happens to the gas? It becomes liquid. So if I don't want my gas to become liquid, if it has to be pure gas, then I have to define the temperature. Now, example, water vapor. Then I will define the temperature. I am having the water vapor in my hand at 120 degrees Celsius. Because if I tell I am having water vapor in my hand at 70 degrees Celsius, nobody will believe. Because at 70 degrees Celsius, what happens to your vapor? It becomes liquid. Is it not? So I have to compulsorily tell temperature to somebody who is asking. Okay. So you try to understand this like this. Somebody is asking you at what temperature you are having this equilibrium in under consideration. If you can tell without telling temperature, still I can define the equilibrium, then temperature is not a variable. Like that. Okay, coming back to this example. Then I should tell him, your friend who is asking, temperature is 120 degrees Celsius, example. But is it sufficient? No, because pressure also has the effect on gaseous phase, is it not? At 120 degrees Celsius, if you apply high pressure, what happens? Still it will become liquid, because we know gases when compressed become liquids. Not possible. Therefore, if I tell I have water vapor in the container in my hand, then I have to tell at this temperature I am maintaining the bottle. At this pressure I am maintaining the bottle of water vapor. If I leave out any one of this, either temperature or pressure, then I cannot completely tell, I cannot confidently tell that it is still water vapor. It could have become liquid, it could have become solid, I don't know. Therefore, a single phase like water vapor has 2 degrees of freedom. That means you have to specify pressure value, you have to specify temperature value. If you don't specify that, then you are doubtful whether it is still water vapor or something else, liquid or solid. So it is having 2 degrees of freedom. Okay, you can ask me a question here. There are 3 variables, like why are you not telling the volume? I am not telling the volume because through gas law, if I tell the value of pressure, if I tell the value of temperature, using PV is equal to RT, the volume becomes automatically fixed. Okay. Or you can just tell temperature and volume, pressure becomes automatically fixed. Okay, fine. So 2 variables are the minimum number of variables I should tell, so that I can define gaseous phase completely. Okay. Now let us add one more phase into this equilibrium. Of course, there was no equilibrium in the previous example. Let us set up an equilibrium by adding one more phase. Which is that phase? Water phase, liquid water. Now, liquid water and gaseous phase is having how many degrees of freedom? This is the question. Okay. You have to, of course, you have to tell at what temperature this is happening. Okay, that's all. Liquid at, okay, now at atmospheric pressure, 1 atmosphere. What is the temperature at which this equilibrium exists? Water vapor and water equilibrium exist at atmospheric pressure. I am telling. Okay, at 1 atmospheric pressure. What is the temperature at which this equilibrium exists? Of course, 100 degrees Celsius. 100 degrees Celsius. So now you see the way I am telling this. If I am telling this equilibrium is at 1 atmospheric pressure, do I have to tell you the value of temperature? No. Why? It is automatically understood. It happens only at 100 degrees Celsius. Any other temperature lower than 100 degrees or higher than 100 degrees, one of the phases will disappear. If you bring it lower than 100 degrees Celsius, it becomes liquid water. If you go above 100 degrees Celsius, all water molecules will become water vapor. Therefore, I just have to tell pressure. 1 atmospheric pressure, this equilibrium is established, temperature becomes automatically fixed. Or it can be on the either side also. You can fix the temperature. Okay, now how to fix the temperature? Can I set up this equilibrium at 50 degrees Celsius? So the question is very important question. Can I set up this equilibrium, water plus water vapor, at 50 degrees Celsius? I can. How? Then I have to decrease the pressure. It cannot be at 1 atmosphere. It should be much lower than 1 atmosphere. Okay, you see the point now. As I try to fix the temperature, pressure will automatically become the variable. If I fix the pressure, temperature will become variable. So how many number of independent variables do you require? Single. Either you fix the temperature or you fix the pressure. So that is what we tell. The number of degrees of freedom for this system is 1. F is equal to 1. Okay, now I'll make it a bit more complicated. I will add ice to this equilibrium. So what is your equilibrium? My first slide. Ice, water, water vapor. At what temperature this equilibrium can exist? At what pressure this equilibrium can exist? We will study the phase diagram for water later. This can exist at a single value of temperature and a single value of pressure. You cannot vary the temperature. You cannot vary the pressure. So that becomes non-variant system. That means all variables are fixed. There is all parameters, temperature, thermodynamic parameters are fixed. You cannot vary any one of them. If you try to vary any one of them, your equilibrium is disturbed. Okay, so that it becomes non-variant. Okay, that is what I've been talking of in this. This is what I've explained in my previous slide. Okay, now let me go to the conclusion of this explanation on degrees of freedom. These are the 3 important conclusions. What are the 3 important conclusions? The greater the number of components in a system, greater is the degree of freedom for the given number of phases. Okay, greater the number of phases, smaller is the number of degrees of freedom. We found it right. In single phase water vapor, what were the number of degrees of freedom? F is equal to 2. If I added another phase to it, liquid water, the number of degrees of freedom came down to 1. If I added the last phase, the solid phase, the number of degrees of freedom F is equal to 0. So as you increase the number of phases, the number of degrees of freedom come down. It's very important. It's very important to understand the phase diagrams later. These 3 conclusions. And greater the number of components, greater the degrees of freedom. How? Because again, for number of components greater, I mean, these are a bit complicated systems. This happens you like calcium carbonate decomposes to calcium oxide plus carbon dioxide. Anyways, you just understand this specific example. One example is there to study by altering the number of components later. That we will see when we take up specific examples. Now, the last one, the number of phases is maximum. The number of degrees of freedom is 0 for the given number of components. Another important conclusion. For the given compound, if you put all phases in equilibrium, like for the given compound water, I have put solid, gas and liquid in equilibrium, then the number of degrees of freedom is 0. F is equal to 0. So for the given system, if all the phases of the given system are coexisting in the equilibrium, automatically F becomes 0. So what does it mean? There is only one magical point of temperature and pressure in which you can see all phases of the given system. If you deviate from that magical point of value of temperature and pressure, one of the phases will definitely disappear. Okay, so this is what I just wanted to tell in this class. So what I've told you in my what have we discussed in this class? We have just built a better understanding of the terms used in phase rule. F is equal to C minus P plus 2. What is F, what is C, and what is P? The next class we will derive phase rule, and then later we will take up specific examples and construct phase diagrams for those examples.